Welcome to Shanti-Peace for Mathematics. In my previous video, we have talked about the chain rule for partial derivatives, which tells you that if you have a z, which is a function of two variables x and y, and if your x and y are functions of one variable t, then you will have this t diagram, that is z is a function of x and y, and x and y are the functions of t. So you can talk about the derivative of z with respect to t, which can be represented as del z by del x dx by dt plus del z by del y dy by dt. We also have discussed that if z is a function of xy and if x and y are the functions of uv, then you can talk about the partial derivative of z with respect to u and v. So for the t diagram for that can be represented in this manner. So z is a function of x and y are the functions of u and v. Since you will have u at the two places, you have to go along with the two paths. The one in this way, another one is this, and here this is the two paths you will have. So that's why you will have del z by del u can be written as del z by del x by del u, that is via this and then this, plus del z by del y into del y by del u. The another path that you have, that is via this one and then this, here this and then this, so that's why it is del z by del v. We can talk about the derivative of z with respect to v as del z by del x into del x by del v plus del z by del y into del y by del v. We have discussed these formulas and proof of this. Here in this video, we will discuss about many examples on this chain rule for partial derivatives. So let's start with the first example. If you have a z which is a function of e power ax plus by and f of ax minus by, then the question is to prove that bzx plus azy equal to 2 times abz. Zx is nothing but the partial derivative of z with respect to x. For the solution, let us consider this. U is a function of ax plus by and v is the ax minus by. Now what is the situation you will have? So your z is nothing but the e power u f of v. So you will have this z is a function of two variable u and v, and u and v are the functions of two variable x and y. That is the situation here you have. So that's why the partial derivative of z with respect to x is via two paths. One is this path and this path. The another one is this one and this one, because x is at the two places. So that's why del z by del x can be written as del z by del u into del u by del x plus del z by del v into del v by del x. So you just see this, and that is equal to del z by del u. So derivative of this quantity with respect to u will gives you e power u f of u. Del z by del x will gives you the derivative of this with respect to x, so that will gives me a, plus del z by del v will have the derivative of this quantity with respect to v. Power u as it is, derivative of f v is f dash v, and the derivative of this with respect to x, and the derivative of v with respect to x will be taking the derivative of this quantity with respect to x, that is into a, and you just note that this e power u is common out, a is also common. Inside bracket we'll have f of u plus f dash of u. Now in similar manner you will have the another quantity, that is in this it is zy. So zy is the partial derivative of z with respect to y. So here also we have two paths, one via this one, another via this. So that's why it is del z upon del u into del u upon del y plus via this one and this one. So that's why it is del z upon del v into del v upon del y. Now again by taking the derivative with respect to u of z, so that is e power u f of u and the derivative of del u by del y, that is a derivative of this quantity with respect to y, will gives me b, plus e power u f dash of v in the similar manner as del z by del v is there, and the del v by del y by taking the derivative of this with respect to y will gives me minus b. So you just simplify that and common out e power u into b, and inside bracket you will have f of u minus f dash of u. Now the question is to compute, so I am starting with LHS side, that is b zx plus a zy, so that is equal to the zx we have calculated as this value, b into e power u into a f of u into f dash of u plus a fy, zy we have calculated as this value, so that is plus a zy we have calculated as this value, so that's why e power ub f of u minus f dash of u, and you just see that e power u is common out from this, a into b is also common out. Finally you will have e power u a into b inside bracket f of u plus f dash of u plus f of u minus f dash of u, and this f dash of u will get cancelled, so that's why it is the final, you will have 2 times e power u into ab. So that is the RHS. So that's completes the proof of this result. Let's have the another example. If u is equal to f of r, where r square is x square plus y square plus z square, the question is to prove two things. Then prove that the first one, del u by del x square plus del u by del y square plus del u by del z square equal to del u by del r whole square, and second one is del square u by del x square plus del square u by del y square plus del square u by del z square equal to f double dash of r plus 2 by r into f dash of r. Here in the output you will have the two things. One is the first derivative is involved, another equation having the second derivative is involved. And what is the situation? U is a function of r. So the situation is this: u is a function of r and r is a function of 3 variable, that is x, y and z. So ultimately your u is a function of 3 variable. If you want to calculate the derivative of u with respect to x, that is the du by dr into del r by del x, because this u is only functions of one variable, so that's why it is du by dr, and then r is a function of 3 variables, so that's why it is del r by del x. For to calculate this, I need to first calculate what is del r by del x. So for that we have given is r square is equal to x square plus y square plus z square. So taking the partial derivative with respect to x, we'll have 2r del r by del x. By using the chain rule, we have on this side we have 2x. So this will implies that del r by del x is x by r. Since this r square is a symmetric with respect to x, y, z, in the similar manner we also have del r by del y as y by r and del r by del z as z by r. Now let us calculate del u by del x. As I have already discussed, del u by del x is represented in this manner, so that is du by dr into del r by del x. But what is u? U is a f of r, so that I can represent as f dash of r, derivative of u with respect to r, and this del r by del x we have calculated as x by r, so that's I am writing here. And in the similar manner, del u by del y, it can be obtained as y by r into f dash of r, and del u by del z can be obtained as z by r into f dash of r. Now the question was to compute this del u by del x square, del u by del y square, del u by del z square equal to this. So I am just starting with that side. So LHS, that is del u by del x square plus del u by del y square plus del u by del z square. So del u by del x, according to this, it is x square upon r square f dash square whole square plus y square upon r square f dash whole square plus z square upon r square f dash r whole square. So just substituting that values from this 3, we'll have this. Notice that this f dash of r whole square upon r is common out from this 3 quantity, and you will left with x square plus y square plus z square, and given that x square plus y square plus z square is r square, so that will cancel with this, and finally you will have f dash of r whole square, and the f dash of r is nothing but the du by dr. So that completes the proof of the first equality. Now for the second equality you have to take the partial derivative again, because in the second equality calculate the second order partial derivative, that is second order partial derivative of u with respect to x, with respect to y, and with respect to z. As we have here, del u by del x is equal to x by r f dash of r. I'm taking partial derivative both side with respect to x will gives you del square u by del x square, that is del by del x of x by r f dash of r. Here you must note that this x is a function of x, this f dash of r is also a function of x, and r is also a function of x. So for that you have to use the product and division rule both. So first I am applying the division rule, so that is denominator square, denominator as it is, the del by del x of x into f dash of r in minus x into f dash of r as it is, del r by del x, that is a derivative of x r with respect to x. This will gives you r. Here I have to use the product rule. So first derivative of x, so that is f dash of r as it is, and the derivative of x with respect to x is 1, plus x as it is, derivative of this f dash of r with respect to x will gives you f double dash of r into del r by del x by using the chain rule, minus x into f dash of r into del r by del x on r square. This bracket is closed here. Now what is del r by del x that we have computed, that is x by r. So let us substitute that value. So this will gives you r into f dash of r plus x into r f double dash of r into x by r minus x into f dash of r into x by r upon r square. So r square is already there here. Now this r is cancelled out, and this x into x will become x square, so that is r, and I am taking LCM for this r also, so that is r square f dash of r plus x square r f double dash of r minus x square f dash of r upon r cube. So this is del square u by del x. Since u is a function of f of r and r is actually r square is x square plus y square plus z square, since this u is actually a symmetric function with respect to x, y, z, so if you replace this x value of x by y, then you will have the derivative, partial derivative of this with respect to y, which is in second order, as r square. So we can write similarly, we have r square f dash of r plus y square r f double dash of r minus y square f dash of r upon r cube, and del square u by del z square is also, we have r square f dash of r plus z square r f double dash of r minus z square f dash of r upon r cube. Now adding these three equations, what we will have, del square u by del x square, del square u by del y square plus del square u by del z square equal to, see, first you should note this r cube is the LCM for all these three equations. This r square f dash of r square f dash of r, and r square f dash of r is coming 3 times. So this is r square f dash of r. Here r f double dash of r f double dash of r f double dash of r is common out. So that's why it is x square plus y square plus z square r f double dash of r minus, here you just note that f dash of r is common out, and inside bracket you will have r x square plus y square plus z square into f dash of r. Finally, what you will have is 3r square f dash of r plus r cube f double dash of r minus r square f dash of r upon r cube. You note that these two quantities are same, so that's why it is 2r square f dash of r plus r cube f double dash of r upon r cube. So that is equal to 2 by r f dash of r plus f double dash of r. So that completes the solution for the second example also. Let's have the third example. If u equal to x square plus y square plus z square raised to m by 2, then prove that uxx plus uyy plus uzz equal to m into m plus 1 u m minus 2 upon m. So it is the example of similar type as we have above. Solution for this, let us consider r square equal to x square plus y square plus z. So therefore u is actually r square power m by 2, so that's why it is r raised to m. So here the situation, u is a function of r and r is a function of three variable, that is x, y and z. We can talk about the del u by del x. So del u by del x is nothing but the u is a function of r only, so that's why it is du by dr into del r by del x. Du by dr, that is the derivative of this with respect to r, is m r raised to m minus 1. Del r by del x, as we already discussed in the above example, that is x by r. So this is nothing but the m x r raised to m minus 2. Now the question is to find out of uxx, that is the second order partial derivative. So here the first order partial derivatives are computed. So now the second order partial derivative, that is del square u del x square, that is nothing but the uxx, which is equal to derivative of this with respect to x. So applying the product rule in this two term, x as it is, the derivative of r raised to m minus 2, it is m minus 2 r raised to m minus 3 into del r by del x plus r raised to m minus 2 as it is into derivative of x with respect to x is 1. So that's why we have this, and this will simplify as m x m minus 2 r raised to m minus 3 into x by r, because del r by del x is x by r, plus r raised to m minus 2, and just you note that this r is cancelled with the one r is here, and you may write this is as m into x square m minus 2 r raised to m minus 4 plus r raised to m minus 2, and you note that this r raised to m minus 4 is common out, so that's why you will have it is m r raised to m minus 4, inside bracket is left is x square m minus 2 plus r square. This is uxx, and you know that this r is nothing but the x, r square is nothing but the x square plus y square plus z square, and since this is a symmetric about xyz, we write similarly uyy is m r raised to m minus 4 y square m minus 2 r square, and uzz is m r raised to m minus 4 z square m minus 2 r square. Now if you add this all the three equation, that is uxx plus uyy plus uzz, this m into r raised to 4 is common out. Here inside bracket this x square plus y square plus z square you will have, and this m minus 2 will be common, and here it is r square and r square, so that's why it is 3 times r square is there. So finally you will have m r power m minus 4, x square plus y square plus z square is r square, so that is m minus 2 plus 3 r square, and if you know that this r square into minus 2 will add with the 3 r square, so that will gives me m r power m minus 4 m r square plus r square, and you just note that this r square will get common. So that's why it is m into m plus 1 into r raised to m minus 4 plus 2. So that's why it is m into m plus 1 r raised to m minus 2. Here u is equal to r raised to m, and that's why r is equal to u power 1 upon m, and so that's why this is m into m plus 1 u power 1 upon m whole power m minus 2, and that's completed the example as this is required to prove. Let's solve one more example here, that is the fourth example. If u is equal to log of x cube plus y cube minus x square y minus xy square, then prove that uxx plus 2 into uxy plus uyy equal to minus 4 upon x plus y whole square. So here what is the situation? If you consider this is as some function, let's say r, then you will have log of r, where r is x cube plus y cube minus x square y minus xy. So here the situation is this: u is a function of r and r is a function of two variable x and y. So we can have the derivative of u with respect to r is du by dr into del r by del x. du by dr is 1 upon r. Del r by del x, that we can compute from this, it is 3x square minus 2xy minus y square. We need to calculate what is uxx. So uxx is nothing but the partial derivative of this with respect to x second time. By applying the product rule, we have 1 upon r as it is, and the derivative of this quantity is 6x minus 2y plus this 3x square minus 2xy minus y square as it is, and the derivative of 1 upon r is minus 1 upon r square. Again, the derivative of this r with respect to x is del r by del x is there. So finally you will have it as 1 upon r 6x minus 2y minus 1 upon r square 3x square minus 2xy minus y square, and del r by del x we have already computed it is the same quantity, so that's why it is a square. Now uxy, it is actually del square u by del y del x. So we need to calculate the derivative of u with respect to y again. So this 1 upon r as it is, the derivative of this with respect to y will gives you minus 2x minus 2y plus this 3x square minus 2xy minus y square as it is. The derivative of r is 1 upon r square minus into del r by del y. Now this 1 upon r minus 2x minus 2y as it is, this is minus 1 upon r square 3x square minus 2xy minus y square as it is. Derivative of r with respect to y. What is r? We have it is x cube plus y cube minus x square y minus xy square. So the derivative of this with respect to y will gives you 3y square minus 2xy. And finally we have uyy to compute. So that's why I need to calculate what is du by dr into del r by del y, and du by dr is 1 upon r. Del r by del y is we already just calculated, that is 3y square minus x square minus 2xy, and uyy again by applying the product rule, that is 1 upon r as it is. The derivative of this with respect to y will gives you 6y minus 2x minus 1 upon r square, because the derivative of r is minus 1 upon r square, del r by del y, and this quantity is as it is. Now del r by del y, it is the same quantity, so that's why it is 1 upon r 6y minus 2x minus 1 upon r square 3y square minus x square minus 2xy whole square. Now the LHS is given is uxx plus 2uxy plus uyy, that you need to compute. You just note that 1 upon r is common out from each of these terms, and here it is 6x minus 2y. It is 2 is multiplied with this quantity, and this quantity is as it is, so that's why we have 6x minus 2y. Then it is 2 is multiplied to this, so that's why it is minus 4x minus 4y plus 6y minus 2x minus 1 upon r square is common out from this quantities that we have this. Here we have this quantity in the terms of uxx, so it is 3x square minus y square minus 2xy whole square plus 2 times 3x square minus y square minus 2xy, because this quantity should multiply with 2, and into 3y square minus x square minus 2xy whole square plus 3y square minus x square minus 2xy whole square is over, and you just simplify this. This is 6x will cancel with this 6x, and 6y is cancel with this one, so this is the first term is 0. It is minus 1 upon r square is there, and you note that this is, so it is of the form a square plus 2ab plus b square. So this is simplified, so this is 3x square minus y square minus 2xy plus 3y square minus x square minus 2xy whole square, and you just note that this quantity will gives you 3x square minus x square, so that's why it is minus 1 upon r square, 2x square plus 2y square minus 4xy whole square. So this is gives you minus 2 is common out, so it is 4x minus y whole square upon r square. What is r? Value of r is x cube plus y cube minus x square y minus xy square whole square. Now you just note that this is x cube plus y cube minus x square y minus xy square. From this two term, x square is common out, so it is x minus y, and from these two terms y square is common out, so that is y square y minus x. So we'll have this is equal to x minus y and x square minus y square. So this is nothing but the x minus y square into x plus y. This denominator quantity can be written in this form, so it is minus 4x minus y square upon x minus y square x plus y and whole raised to square. Here you will have 4 because this is x minus y whole, so here it is 4, and finally you will have this x minus y power 4 is common out and it cancel. Finally you will have the answer is x plus y raised to square. So in this video we have solved 4 examples of partial derivatives which involve the chain rule in it. I will suggest that you go to my lecture notes and solve. There are various other examples is given as an exercise. You may solve it. Once you solve it, the idea about this chain rule is clear. That's it for this video. If you like this video, please press the like button. If you have any suggestions, comments or a question, please drop down in a comment box below. See you in next video. Till then, bye bye, sayonara.